Ready? Wait, scoot over a little bit. Go that way. Gotcha.
Hi, my name is Nick Sherwin.
And I'm Brian Holdeman.
I'm Joseph Schaefer, and today we're going to teach you how to do a problem that was assigned to us using the impulse momentum theorem.
We hope you enjoy watching.
A thin ring and a homogeneous circular disk, each of mass m and radius r, are released from rest on the inclined surface. Assuming they roll without slipping, determine the ratio of the velocities of their centers and their angular velocities after t equals 5 seconds. If they were released simultaneously side by side on the plane, which would be in front when t equals 10 seconds, and what distance would separate them?
The first problem we had to address was finding the ratio of the velocities after 5 seconds. In order to do so, we set our x-axis parallel to the slope and the y-axis perpendicular. First, we used the equation for impulse momentum for each the ring and the disk. We found that in each of our impulse momentum equations, we had one equation and two unknowns, which were the force of friction and velocity after 5 seconds. Therefore, we determined that we needed to use kinematics to find friction.
Using kinematics, we summed the forces in the x direction for the ring so that it equaled mass times acceleration, which in turn equaled w sine theta minus the force of friction. During the algebra of this equation, we found that we needed to solve for alpha, so we used moments about the center, which equaled ig alpha, which gives us the radius times friction equals mr squared alpha. In terms of friction, we found that alpha equals friction divided by mr. Then plug the alpha back into the force equation. We found the force of friction of the ring equals mg sine theta over 2.
Going back to the impulse momentum equation, we used our newly found force of friction, which equals mg sine of theta over 2, and plugged it back into the equation. This gave us 5w sine of theta minus 5 times the force of friction equals mass times velocity. After doing the algebra, we solved for Vg and found it to be 2.5 g sine of theta.
Now for the disk, we use I equals 1/2 mr squared and then solve the kinematics with the same method as we did for the ring. From the force equation, we find the force of friction to be mg sine theta over 3. After plugging that back into the impulse momentum equation, we find the velocity of the disk to be 3.33 g sine theta.
To solve for the ratio of velocities, we divided the velocity of the disk from the velocity of the ring as shown. This resulted in a ratio of 3/4. In order to solve for the ratio of angular velocities as assigned in the problem, we used the relationship between velocity and angular velocity, which is v is equal to r times omega. With simple algebra, we were able to solve for omega of both the ring and the disk with the previously found velocities. This resulted in the same ratio of 3/4.
For the last question, we needed to solve for the distance between the two after 10 seconds. First, we used the equation of constant acceleration to find the distance the ring had traveled. We completed this by plugging in w sine theta over 2mr for alpha and found the distance traveled to be 25g sine theta.
For the disk, we used the same process except alpha was 2g sine theta over 3r. After plugging that alpha into the constant acceleration equation, we found the distance traveled to be 33.33 g sine theta. As you can see, the disk traveled further, and to get the distance between them, we subtracted the distance of the ring from the disk, which we found to be 8.33 g sine theta.
Professor Shenton, thank you for watching. We put a lot of blood, sweat, and tears into this project.
Again, thank you for watching. You're the best dynamics professor we've ever had.